and the idea of a centre. There are no such in these models. They have no centre and no boundary. People at this point, when I teach relativity, often say, well, that's kind of hard to get your head around. How can it possibly be? Wasn't the universe very small early on? The answer to that question is yes. But the answer to the question of whether it didn't all start from a point like an explosion is no, that's not right. Again, going back to the ideas of Eddington, most people in this room, I'm sure, if you have an idea of an explosion, what comes into your mind is something like a bomb going off, with pieces flying away from some localized center, something like a hand grenade. Okay? There's nothing wrong with that, except that it's not that kind of explosion which is involved in the Big Bang. The closest analog, if you want to use those terms to describing the Big Bang, is something like, you have to imagine that the early universe was full of bombs, say hydrogen bombs, all wired up. And then, by some mechanism, they were all detonated at the same time. The bombs spread everywhere throughout space. There is no boundary, and therefore no center. So the whole thing gets triggered. There's a massive eruption of energy, but it's the same everywhere. It's not the same as a hand grenade being thrown that explodes at some point. Of course, that's the conventional way of doing it, but that's the product of us always being presented in our lifetimes by walls, living in buildings with walls, etc., etc. It's a way of thinking that has become ingrained in us, and which one has to get rid of if you really want to do general relativity. So this parameter S measures a scale and not a radius. Of course, it increases as time, and I've shown here several ways in which it can go, depending on a constant which comes into the theory. Let me take the simplest case first, k equal to 0. It corresponds to the situation in which the kinetic energy, the explosive motions of the particles, is exactly balanced by their tendency to pull each other together. Because, of course, every galaxy in the universe has got some mass, gravitational mass. They're all trying to pull each other together. It's not their natural state to be exploding away from each other. They are, because of the Big Bang. But clearly, you've got two countervailing forces, one of which is trying to expand, and the other one is trying to collapse. If you've got a perfect balance between these two concepts, then the universe will follow this path. And eventually, everything will run down like a clockwork left with no energy, and eventually everything will come to relative stability. Not a very interesting future, but that's one of the possibilities. If, on the other hand, you were on this track here, labeled k equal to +1, you would have more power associated with the tendency of things to pull themselves together than you would have with the kinetic energy where they're all trying to rush apart. At some point then, it has to happen that they will stop rushing apart. So they will rush apart up here, they'll slow down, eventually everything will be instantaneously at rest, and then everything will rush back together. And if there was no dissipation of energy, no entropy, then it would rush back along exactly the same path going down there as it had going up here. All right? It would have to be symmetric if there was no dissipation. The other possibility, at least conceptually, is it could be on a track like this, labeled k equal to -1, which corresponds to the case in which the kinetic energy, the energies of the motions, is bigger than the gravitational energy. Now, that kind of universe is not going to ever collapse back on itself, and it's not going to run down. It's just going to keep going. And if Eddington's right, then each person sitting here can, to a certain extent, make up their own mind about which one they would like it to be. And in some sense, according to the Eddington approach to philosophy, the majority opinion will eventually prevail. We make up the equations of physics to mirror what we know about physics at any given time. And if we are convinced by observations, whatever, that the universe ought to carry on expanding, then it will, if it's described by Einstein's theory, follow this track. Okay? So it will have an infinite future. Now it would be nice, wouldn't it, if I could stand here and tell you which exactly of these tracks our universe is on. I cannot do that because we don't know. But what I can tell you is that it probably lies in between this k equal to 0 and this k equal to -1. So it's going along somewhere in this segment of this diagram. Right, people take this with a lot of faith. Of course, it's backed up by excellent observations. In fact, we're now living in the golden age of cosmology. When I started doing graduate work in Cambridge in the 1970s, doing cosmology was a very shaky thing. I remember one head of department shaking his head and saying, "You don't want to do cosmology, Weston. Nobody knows anything about it. It's just speculation." Well, here we are, and we've got fantastically good data about the rate of expansion, the temperature of the universe, its age, its chemical content. The subject has got a massive, massive input of information over the last 20 or 30 years. We're in the classic age of cosmology, what most people in my field call the era of precision cosmology. When I was a grad student, we didn't, for example, know Hubble's parameter, which describes the rate of expansion of the universe to better than about a factor of 3. The density was unknown to a factor of 100. We now know both of those numbers to very good accuracy. We know what the temperature of the universe is to better than 1 part in 10 to the 5. The perturbations are about 1 part in 100,000. Those are good numbers. Even by the standards of solid-state physics done in a lab, they are good numbers. The reason, of course, why we are proud of this man is because he wrote down equations for cosmology before anybody had made any of these observations. Now, if you think about it, that's kind of remarkable in itself. How can a person, even given the fact that Einstein was quite clever, sit down and in a few pages write down equations which encompass an infinite universe, a universe which is infinite in extent and probably infinite in time? It's a remarkable fact. When anybody reads a book on physics, it's always seemed remarkable to me that in a couple of 100 pages you can write down really all there is to know about physics in terms of its fundamental laws. Of course you can read longer books if you want to, and undergraduates are obliged to read those. I'm sorry, but that's just the way things are done. But really any good book that wants to earn its worth, at least in my view, shouldn't be less than 200 pages, because then the writer feels that he or she is getting shortchanged. On the other hand, the way of I looking at it is that, okay, if it's 300 or 400 or 500 pages, then why the hell is he spending so much time trying to explain all this? It's all supposed to be logical. If he tells me on page 1 what the law is, I ought to be able to figure out the rest by myself. So, to me, the ideal situation about a book, especially a book on physics, is that it should be in between 200 and 300 pages long. I had the privilege this afternoon at your library here to look at the first editions of some of the books that have revolutionized our understanding of physics. So in particular Newton's Principia and the books by Copernicus and Galileo. They aren't long books. And they're still valid. You don't need big, massive tomes to explain things, if it's correct. Beware these books where everything has a kind of exception and you have to go through thousands and thousands of exceptions. If the thing's going to work, then it should be reasonably easy to explain it